Welcome to the pre-recording of lecture 30, which is the second part of the 15th session of MCS 260 in the 8-week summer course in the first day of the 6th week. So we still have 3 weeks to go. This is the beginning of the 6th week. So this still fits within designing large softwares, although like the previous lecture or the first part of the session, we are considering small program, essentially code snippets. That will suffice to illustrate the introduction of exceptions. So the main goal is to write robust programs. Exceptions in Python are essentially classes, and Python already provides a very extensive hierarchy of exceptions. So there are many things that can go wrong during the execution of a program. As we already know and covered also in the first part of the session on software testing. Okay, what's the goal? We want to write robust programs, but so robust program is capable of handling errors. If the user mistypes something, we don't want our program to crash, because it could be that it's somewhere in the middle of a very long and time-consuming interaction. So what is an exception? An exception is an unexpected event that happens during the execution of a program. It's actually interrupting the normal flow of execution. An example is a division by zero. So that's an arithmetical error that occurs. Overflow is another one. The user may provide wrong input. We also have seen the assert statement. So the assertion error is another predefined exception. We define two stages, or we distinguish two stages in the exceptions. An exception is triggered, thrown, or raised. So we make the distinction between raising an exception, which is done on purpose. Sometimes a subfunction may see that there is something wrong with the input and immediately raise an exception. So that could be as part of defensive coding as well. So with the assert statements, that will happen, but perhaps as a programmer, you don't want that these assert statements are ignored when the user runs it with the optimized mode of Python. So you want to raise explicitly the errors, so that can be done. So in the first phase of an exception, when it is raised or triggered, then the second stage, the exception can be handled. So even if, say, a function raises an exception, the caller of the function can anticipate this and write code that handles the exceptional case. So the fact that if you keep in mind that exceptions, they are not an if-else statement, so they are really truly for exceptions. You can still handle them, you can still write programs in a very structured way. So the except is really indicating that here I have an exceptional situation. In real world, we have exceptions. So here to make the distinction between an exception and an if-else. So we live in Chicago, a city full of high rises. And my office is in a high rise, although I use the stairs. So I've observed that, and you all must have observed this, that many people, when they are in a hurry, they are not afraid to stick their hand or other body parts impeding the closing of the doors. So that is an exception of that is an illustration of an exception handler. Normally that shouldn't happen, but elevators have been made so robust that people actually trust this. The older elevators, and you can see them in old movies, they often had an attendant who was opening the doors, and the doors were doubled up. You had an interior door and an exterior door. So first, when people were entering the elevator, the exterior door was closed by the attendant, and then the interior door was also closed. So there was no exception necessary. So it was really um, guarded by the attendant who would get in and who would get out. Okay, um, exceptions are for exceptional situations. Now, if you are in a high rise, you may find it sometimes funny to see how people desperately try to stick um, their body parts to prevent the elevator from closing its doors. But after a while, the elevator might also close its doors extremely slowly. And if you are in the elevator, it might actually quite get annoying. So frequent use and actually misuse then of exceptions should be avoided. So as a programmer, you should essentially realize when to use an if else and when to use an exception. Exceptions are for unexpected events, but typically if you want to build good programs, they are not something extra or as an afterthought. So here are some examples. Division by zero may occur. So we had the um, definition of a rational class. So at the constructor, the user must provide a numerator and a denominator. The default value for the denominator could be 1, so because every integer is a rational number. And you should actually expect that users are rational and they are not going to try all the time to create rational numbers with a 0 denominator. But still, it may happen. And then you should actually trigger an exception when that constructor is called. Prompting for names, prompting for file names. But by the way, we will see later, or we have already briefly touched into uh, web servers. If you write software that is going to process forms, then uh, you want to make your website robust enough. If the user kind of omits a field uh, in a form, even if it's clearly marked, please enter this, this is mandatory. But if the user doesn't do it, you don't want your website to crash. So this is a little bit similar to prompting for a file. When you connect a name with a file, there are two things that can happen. The file does not exist. That's very annoying when you open it up for reading. Or the file may actually exist, but it's also very annoying if it exists and you override it, you open it for writing. So then actually the original file disappears. There is the keyboard interrupt. You may be in the process of a very long and expensive operation. So it may be that you are retrieving data, and this particularly would be in a robust installation. If you have a script that is changing something in the installation, the user is losing patience. So it's a terminal based application, install some software. The user presses ctrl+c. You may want to warn the user that all the work that has been done at to this point will get lost. So do you really want to stop now? So if you set up a web server, sometimes there, also with Jupyter Lab, you have to confirm when you stop the web server. There is a positive application of this handling of the keyboard interrupt. That is an anytime algorithm. So we have seen the Monte Carlo method to estimate pi, and that will actually go on forever. Um, and as an anytime algorithm is an algorithm that, if given more time, more resources, it will improve the result. Here, in this case of Monte Carlo, it will essentially improve the accuracy of the estimate. So in Python, you can easily implement this with the handling of the ctrl+c interrupt. I will illustrate this in the third part of this recording. Um, Exceptions in Python. How do we raise, handle, and define exceptions? So we raise exception with raise. So yet another reserved keyword that as a programmer we cannot use. So in the constructor of um, rational number, you could raise zero division error if the constructor is called with a zero denominator. So that would be indicating the nonsensical, and that would actually also prevent a lot of errors. So you try to handle an error right from the start. So you could say, well, you know what, if the user wants to present 1 over 0, why not? But then the user tries to compute with that number, and there are some errors there. So then you might think that in the methods there is something wrong with the arithmetic on rational numbers. Okay, the second part is the handling. So there is the try except statement. It takes a little bit the form of an if else. But again, a try except is not an if else. So the if else, what you would do is that you would explicitly test on the denominator that is 0. In the try block, you will try your division, and you can actually check on the 0 division error. You can have a sequence of exceptions. You can have also multiple except statements that would give you different um, handlers depending on the type of the exception. We have covered inheritance and classes. So Python is object-oriented, and Python is a framework language. Framework languages are collections of classes. So we will see how the extensive collection of exceptions can be used um, to extend the exceptions. So we make a new class by inheriting from an existing exception. So that's the most. So I had it first defining, raising, and handling, but the definition of an exception we did already. It's the occurrence of an unexpected event. So because Python's exception mechanism is already so extensive, most likely as a programmer, it will be sufficient that you know how to handle, how to write good exception handlers. Okay, so here is the try except statement. So there is Python is block oriented, so the indent is important. So we have the code in the try block. So that is the block where you expect an exception may occur. So that defines the scope of the exception handlers in the except block. So the second part is the accept. We can leave it blank. Then actually it will do something whenever an exception occurs. But you can also actually also perhaps write your exception handlers more efficient, but also more explicit. So in your code, you can then indicate in the code that is in the try block what the exceptions are that may occur. So you can also have multiple except statements where you are trying to see you have different exceptions, and with different codes you can handle different exceptions differently. Okay, sometimes you don't want that exceptions are handled, but that there is still better error message. By the way, try excepts are also quite good for debugging. So in some sense, it could also be a debugging tool. If you have somewhere your program crashes, you see the exception somewhere. With the try, you could, if you have a complicated program, you could try to go in a top-down fashion to see first around in your main program, then in a function, then in a sub-function. You could try to triangulate where the error happens. So the try finally would be very good, or really if the exception cannot be handled in the function where it occurs. In a debug mode, in a more verbose mode, you could actually have the error message that is displayed. So if you want to make your code more verbose, you see somewhere a race that is not handled in a subfunction, you could encapsulate that code with the try finally. And in the finally, you would put your verbose statements. Okay, here is the code, the pseudo code for an anytime algorithm. So there is a loop. We have the initialization of a result. So if we estimate something, our first estimate could just be 0. Then we add to the estimate. So we average over the successful trials. But printing out all the results, it may not show simply too much and your screen will be swamped. Um, Printing every 10,000 steps is tedious, and you may just leave it up to the user. Does the user want to continue or not? So in the keyboard interrupt, the user is shown the result and then prompted to continue or not. Observe the break. The break here does not break in the while through the innermost. So there are two while trues. So in some sense, that seems to be very dangerous code. It is a double while true. So and the computer result has no break in there, so it will continue. But the keyboard interrupt will be noticed by the main in the main loop. So and the exception handler will be triggered. So it will be noticed in the try block. So I should say that it's noticed in the try while the results are computed. And then the break happens when the user types N or anything different from Y. Then the break happens and the break breaks out of the outermost loop. And the program terminates. So that's actually the only way to do this. So typically while true, I would cautiously kind of replace this while, say, the number of tries actually has exceeded. So you should um, or you should at least have a print statement that the user must press ctrl+c to exit. Okay, in Python 2, I had a simple diagram for the exception hierarchy. Python 3 has gotten way more extensive, so there are way more things that can go wrong in the meantime. So here you see that what I copied from the documentation of Python. We have already have already seen the assertion error. So even if you may be annoyed that you're running the program in debug mode and you get all these assertion errors, well, you can essentially ignore them by placing handlers in there. And that could lead to a trial and error. So the arithmetic error, so we've seen the zero division error. The zero division error is a subclass of arithmetic error. It's a subclass of the exception, and it is a subclass of the base exception. So the keyboard interrupt is an exception which is directly under the base exception. All right. I could show, but not on the slides, all the errors, and I must say that I have not used that many of them either. So we have the file exists error and the file not found error. So that is important. That's in the operating systems errors. So there are the broken pipe errors. We may see some of them when we get into the threading. Then there is the syntax error. There is actually a syntax error defined as an exception. So the two syntax error are the indentation errors and the tab errors. So these are the errors that the Python interpreter may throw to you. So there is the type error. So we had the assert which checks on the type. If as a programmer you're really not satisfied with that approach, you suspect that there might be something wrong, or you want to help the user. You could, so we've seen an example of the searching a list for an item. If the parameter is not a list, then you can then the type error will be raised. If you do something with, if you apply an instruction on something that is not of the appropriate type, you could handle this. We've seen the index, so the dot index will give a value error. So with the search item, we tried to capture this in the first part of the session, in the previous lecture. There are plenty of warnings. So if you write your own software and you are giving your releases, in Python you can raise a deprecation warning. So if the user is still using features that you think will become deprecated in a future release, then you can actually raise that error or raise that warning. Okay, exceptions. It's good to raise an exception, so you can raise the main exception in a function when the age is negative, if you prompt for a negative. You can define an exception invalid age with an object data attribute. So I will show with the file not found error how you can print an error message with an argument. Okay, I'm halfway this lecture. Let's move now to the second part. So the exceptions are actually unexpected events. So I will first, in the first subsection, demonstrate, perhaps to make this a little bit more interactive. Let me restart the kernel and clear all outputs. So typically I make the notebook so that you can run them from top to bottom, but now there are exceptions in there. So let me illustrate how to erase an exception. So I have a numerator 1, denominator 0, and I can explicitly erase the 0 division error if the denominator equals 0. So this is useful if you have a constructor in your rational class and some user tries to define a rational number with a 0 denominator. But you can get around it, or if the constructor, if the code, if the writer of the code that calls the constructor wants to pass the bug up, wants to warn the user. So if you have an interactive computer algebra system that it crashes is something pretty bad. So you can handle it. So here it is. So we place the instruction in code cell 3 in the try block. And then the handler is simply saying the denominator is 0. Now, this is writing an exception, and actually, this is still, I mean, it's not angry at you. So here you see these red letters. So you can find this gentler. However, um, it's still an exception essentially. So with finally you print a message, so you can be a little bit calmer than the exclamation point. But you should still raise it because in the construction of, say, a rational number, nothing was done. So the object that will be returned will not be a valid object. So you have to decide then what you will do there. Here I decide to still raise the exception. Okay, that's the start. Um, so you can cause programs to crash now. So there is the hierarchy. So the file not there that we will define will inherit from OS error. So OS error is a subclass of the exception. So, and we can verify this here. We also saw this on the slides. So there is the exception. Um, then there is the base exception, and then there is the very base class, which is called object. OS error has several subclasses. Actually, the file not found error is actually the error which is very similar to the one that we are going to define now. Okay. Um, So you see that there are actually attributes already there, data descriptors, file name too. But let's define it. So here we want to define our own exception, which will be raised when a file is not there, when somebody tries to open a file, whether it is for reading or we can also raise it for writing. Here I'm creating a situation. So first of all, I'm probably too fast. So let me describe what happens in the code cell 8. In code cell 8, I'm defining the exception file not there. So that's an exception that doesn't yet exist. I will put it under OS error. So under OS error, then it can also be handled under that OS error. Um, so um, I will raise it when the OS error happens. So the constructor will actually store the attributes. So defining your own exceptions is very useful also for debugging. So it could be that fixing a bug takes time, but you could always patch it. So if you have an exception that is raised in the debugging stage, you have found a spot where it raised and it's raised there occasionally. You don't have the patch ready yet, but you may already have an exception handler there. So the first exception handler would be simply writing the message you're aware of this. It will be fixed in a later version. It could be that in the design, but that might not be a really good design, that or perhaps it does if it's really an unexpected event, if it happens just once a while. So you could have a dedicated function for this, but that function would need the data. So you, in the exception, you could store the data. So here I'm just going to store a name. So there will be one data attribute. So now it's very good that we have seen inheritance. So we make a derived class. We derive the class file not there from the class OS error. That means that we are instantiating that class. So we are calling the constructor of OSError. And we are adding an additional attribute name. So just some name. It will be the file name. So it will be this file name here. So I made it under very particular. So the slash is the root of the file system. I said not a file.txt. It's highly unlikely that your root contains that file. So there will be an OS error that will be raised. Okay, so now is the execution. So here, what happened? So it's a nested try. So just to simulate this, so the opening would be done in, say, a sub function. So, or during an interactive part of the code where some file name was prompted. So defining the name of a variable is a very useful substitute for an input. So on opening what is defined in code cell 9, opening it for reading. This could be in the normal execution of a program where you expect the user to type in something that exists. But it doesn't exist. So what will be triggered will be the OS error. When it happens, we are erasing our own file not there. And the parameter is the some file name. So that is the innermost block that raised our exception. So we as programmers, we have defined this. So, and because it's a subclass of OS error, it will be handled by OS error when that occurs. So we can then handle it. So this is a very unusual construction, but it's to demonstrate the outside. So typically the innermost block would be somewhere in an innermost function. The except would be happening at a higher level in the hierarchy. We can accept the exception. We accept it to handle it. So we name it the error. So the file not there is the name of the class. The error can be considered as the object with the data attribute name. And then we can print out a message. And then you have the except, and this should also work with the finally. So that will still generate the error. So let me demonstrate this. So instead of the except, I have the finally file not there. Okay, so let's try this. Finally, actually, it doesn't. So the finally, um, well, let's see if I really want finally. So I have the except statement. Let me try if I can have finally over here. Um, I'm improvising. It was on the spur of a moment because I was curious, but here, um, let's see if it's going to do this like this. And the red lettering is because of my wrong indent. Okay, no, it's not a good syntax. So the finally can actually not be used. But I fixed another mistake. All right, that is the part where I tried to be a little bit more interactive, and scrolling through a prepared Jupyter notebook has advances. So I advantages. So I don't really want to do the control C in a Jupyter notebook. So for that part, I go to the uh, PowerShell. So I have the script control C, hold control C to stop, control and then C. Here I was rather slow, so you can use this as kind of a game to measure your reaction speed. But this is also to show, let me now show actually what Control C does. So here is the script. It's very straightforward. So what the script does, it's counting. So in the try loop, in the try block, it goes on to count at 1 to a count. And you can see that when the keyboard error interrupts, it is handled, and it's actually also stopping the program. So it is executing it. Um, and you see my second time around, I was trying to be very fast, but still my computer is quite fast. It reached up to 11 million already. So just to indicate that within our reaction times, computers can do millions of operations and even billions of operations in a second. All right, so this was just a game. Let me now show the anytime pi. So the anytime pi is extending the Monte Carlo simulation, where we are throwing darts. So we have a uniform random number generator, generating numbers in between the square, 0, 1, 0, 1. We count as a success any of those numbers that are landing in the unit disk. So that is this test here. So it's also a counter. So it's just the same program, but now the counter is incremented. Um, you saw when I executed the Control C, the previous script, that the keyword interrupt indeed interrupted the program. But what we're going to do here is the keyboard interrupt is going to be included in a while true. So if the break would not be here at the very bottom of the script, then essentially this keyboard interrupt, the Control C, would never have an effect. So you can actually permanently disable the keyboard interrupt by putting it into a while true. So and you could eventually count also the number of times the user has pressed it, and then perhaps after the 10th time, really closing the program. But this is an application of an anytime algorithm. It will show the current estimate. So let me run it. So it's the anytime pi simulation. Control C. So if I do this very quickly, I have uh, about 2 decimal places correct, or actually only one. So I will continue, Control C. So now I see 3.14. You also see the count as it has done. I continue. I do Control C again, and I see the next estimate. What happens if I now type Control C? Let me try to do this. Okay, so now I am unruly user. So actually, during the handling of the above exception, another exception occurred. So I was tired of it, and actually it did the end of file. So this is another error. So it was actually expecting to give input, it didn't get it, but then there was an end of file error that happened. So it's not the keyboard error that caused the interrupt, but it is the end of file error that caused the interrupt. So as a good user, but at the end of this recording, I don't feel that good anymore. So I wanted to experiment a little bit. So you see that perhaps let me now be the good user. So Control C. Actually, yes. Ctrl+C again. Now yes, Ctrl+C, and now I'm happy about the estimate. I type no. So you can see the number of samples it has taken. I don't want to do that many samples, but you see how the estimate is going. So this allows to monitor the process of an algorithm. So you could have a process that takes on for quite a while. If you are happy doing something, drinking coffee, going out for lunch, you just let the program run. But you're just sitting there and you want to check the progress, well, type Ctrl+C and you could have an intermediate report. So just how you could make useful scripts for anytime algorithms or for very long algorithms. Okay, now I have 4 scripts on the reading of a file. So here you see still the I/O error, and I should have fixed this. So this is the OS error. It will still run. So the OS error was essentially Python 2. So I developed these scripts when it was still Python 2. I checked the OS error still works. The I/O error still works, but it's actually not documented in Python 3.11.4, so it might get deprecated already there. So here you see a classical example. We try to open a file for reading. If it's there, then it will just work. If not, it will give just simply write, give me an error. So I just saved this. So this is my first read file name. So there is a readme in my folders, opened it for reading, so very fine. I use the underscore, but here actually it opened, but it raised the file not found error. That is interesting. So I should have so I didn't fix it right. So the OS error did not work. So it was the file not found error that should have been used. Okay, so let me do that again. And now it raises the file not found error. So now I'm actually a little bit suspicious. It raises the file not found error, but I actually had expected that it would actually handle it, but it doesn't do it. Well, let me go to the next script. Actually, oh, I'm sorry. So this is actually the script that I was running. So my naming was wrong. So the read file name is actually the script that I should have been running. README, the README does not exist. So that is what it is. And I think OS error would have helped as well. So here you see the second one where I'm still having the I/O error, but I will replace it now by so this is read file name 2. So try again, yes, readme exists. Readme does not exist. Well, I now made a genuine typo error, so you see it's late in the evening. Okay, so now it works. So this is how you make more robust scripts. I have one last script. So this is the more extensive one. So this is where I have the file not there, and I still have an OS error sitting in there. So I make these pre-recordings also in preparation of my lectures. Okay, so this is it, the third script and final script. So let me do the README. Everything is fine. Let me now run this with another file. The file README does not exist. And that code gets, so you could say, well, what's all the fuss about? Well, the error messages are the same except for the question mark that I don't have here. Here I have now opened it up. Here I have the object again. So the class definition. So here I have the object ERR, abbreviation for error. And I can select the data attribute name. So this is useful in situations where you want to pass the data to the exception handler. Could be a strategy for debugging really exceptional situations. Okay, let me conclude with this, going back to the uh, slides, perhaps what we have seen. So the purpose of this lecture is always that you can start on the exercises to write more robust scripts. This is very useful if you're ever going to design websites, if you are going to write scripts that are going to process user input that is given through forms in the internet. So often these forms are used to fill in databases, and having good exception handlers there is very important to avoid that your database contains inconsistent data. Okay, I hope this lecture was interesting. So it's the middle lecture in a week about programs. In the next lecture, we will talk about complexity. So we have the anytime algorithms that go on forever, and they will give us better results, but they are a member of the problems that you typically handle with these anytime algorithms are extremely hard problems. And we will talk about complexity in the next lecture. So in the previous lecture, in the first half, we talked about software testing. Here we talk about a very much related topic, exceptions to make scripts more robust. In the next lecture, we will talk about timing programs that you can monitor the resources being used by your program. Okay, I hope this was interesting. I stop the recording now.